I was working on many different AStable multi-vibrator circuits. This is one of the circuits that I made. It was published on my YouTube channel, but not in this form. Anyway, perhaps I will give the link. And here is another circuit that I made, AStable multi-vibrator, with all these knobs. This was published on my YouTube channel. I don't want to make this video too long. So this is the front of that new circuit anyway. And of course I was working with a voltage controlled oscillator circuit, and that's here. Also in a certain way useful. The schematics are also on YouTube, but now I also wanted to experiment with an op-amp. At first I thought that this op-amp was a 555 chip. Well, that was not the case. It is this chip, the NA5532B. I thought it was the classical 555 timer, but that was not true. Studied it, of course, before the moment that I wanted to publish that on YouTube. Of course, I must absolutely be sure that circuits work when I publish them on YouTube anyway. This is the schematic now. I don't know if it is a expensive op-amp or a very cheap op-amp, etc, etc. The frequency is set here via the capacitor value, going from pin 2 to ground. That's of course ideal. And here is a demo. At the moment I've used here 47 microhenry microfarad, of course, here microfarad. And now we have this frequency. Does it look nice? Well, I think it looks quite good, given the simplicity when using such a simple op-amp. Of course, this is not, say, a pure straight square wave, but anyway, it works on 10 Hertz, 12 Hertz, 14 Hertz. Well, it's a little bit unstable. That could have to do with my counter. Switch on a new counter, other counter. Let's look what this counter tells us. It's 11 or 10 or 11 Hertz. Well, not bad, I think, when you want to do experiments. Anyway, I now, here the circuit again, I now disconnect here with the pliers this 47 microfarad cap. So now it's disconnected, and now we have the situation that we can choose between 100 nanofarad here and 33 picofarad. Of course, that are, say, enormous different values, but, and it also means, of course, that we have very different frequencies, because this is the time dependent capacitor, given here the situation inside the op-amp and the resistors that I've used here. 47K, so you can also replace it by a 100K resistor, and also here from pin 1 to pin 3 a 100K resistor anyway. But what will happen when we use here a 33 picofarad capacitor or a 100 nanofarad capacitor. At the moment we are with the 33 picofarad capacitor, we are on 262 kilohertz. That's not bad for a op-amp. And say the square wave is changed into a triangle wave. Anyway, not bad. You can surely use this for all kinds of electronics purposes. And now we switch to 100 nanofarad, that is 0.1 microfarad, and well, now we are on 4.55 kilohertz with a beautiful waveform. So this is, say, a kind of way of demonstrating a circuit, and especially the properties of this op-amp. It will go surely from, say, 30 Hertz up to 258 kilocycles. On 258 kilocycles you will surely see that it is not a square wave but a triangle wave. And that's more or less all to tell. Thanks for watching. Schematic again. Let's look again on that waveform. Very undistorted waveform. So this is perhaps a better view. 4.5 kilocycles. Surely such a waveform is usable for all kinds of purposes. And of course, when you use here a rotary switch, you can switch to different frequencies. Say going from 30 Hertz here up to approximately 250 kilohertz, when of course you have a rotary switch with one mother contact here and then 10 other contacts, and then use different capacitor values. It surely can work, will work, and it's simple.